Welcome everyone. In this lesson, we're going to be looking at some more rules for calculating derivatives. And these are going to be the kind of the quick derivative rules. And we're going to be using these a whole bunch. And so far, we've seen the limit definition of derivative, and we've seen what the derivative actually is, and that's a pretty involved process to actually calculate. But we've also seen something like the power rule, which was quick, which allowed us to quickly differentiate something. And so just review over the power rule, where we had x raised to the power r. And to calculate the derivative of that power function, what would we do? We'd bring down the exponent, we'd keep x the same, and then we'd subtract 1 from the exponent. So we'd get r times x raised to the r minus 1. That was the power rule. And so far, that's all we've been able to differentiate. But now we're going to start looking at some more basic derivative rules that are going to allow us to differentiate some other things. And so the first one of these is the constant multiple rule. And essentially what this says is if we want to differentiate, so that's what that d dx means, it's just calculate the derivative of what's inside the brackets here. If we want to differentiate where we have a constant k times some variable terms, f of x, well, what we can do instead is we can focus in on just differentiating the variable part, and then once we have that all finished, we can multiply the result by k. So really, we have a constant times some variable stuff, and we're trying to differentiate the whole thing. Well, what we can do instead is differentiate just the variable part and then multiply the result by k. And that's what this constant multiple rule really says. So it's important to kind of make the distinction. What are we going to actually have here? Well, this is a constant k we're multiplying, so there's some multiplication. So we're taking a constant and we're multiplying it with some variable terms. F of x. So this is what a constant multiple, kind of the constant multiple of a function is. We have a function times that constant. So as a quick little example, kind of a special case then of the power rule is if we have, say, the function well, let's make it a k just because we're using k already. K times x raised to the power r, where k is just a constant. Well, how we're going to differentiate this thing is, if we're going to differentiate, well, what we're going to do is we're going to just differentiate that power function just like we normally would. So what do we get? Bring down the r, keep x the same, subtract 1. So we get precisely that. And then this constant k that's in front, well, it's just going to stay there in front. So we're also going to have a k right in front there. And that's what this constant multiple rule is going to kind of help us do. It's just going to allow us to differentiate just a bit more functions. So let's try an example. Let's look at example 1, and we're going to look at these two. So we have, in the first one here, we're going to differentiate the function 2 times x raised to the power 5. And what we have here, this is a constant multiple. We have a variable term, x raised to the power 5, times this constant 2. So this is a constant multiple. All right, so what does that rule, what does that constant multiple rule actually tell us? Well, it tells us we can focus in on differentiating that variable part. So this x raised to the power 5, let's just get the derivative of that. So I'm going to differentiate that just like normal. So I'll bring the 5 down, keep x, subtract 1 from the exponent. So I get 5 times x raised to the power 4. So that's my derivative of the x to the power 5. And then what happens with that constant multiple, that 2 that's in front? Well, it just kind of stays there in front. So we have the 2. And if we want to clean that up, 2 times 5 is 10. So we end up with 10 times x raised to the power 4. All right. So that's the idea with constant multiple rule. The constant multiple just kind of sticks around in the derivative. Well, let's try another one. Let's try the second one here. We're going to do the derivative. That's what this means. Of everything inside the parentheses. And our function this time is x cubed divided by 4. Now, for this one, it's not quite written in the correct format. So I'm just going to slightly rewrite the function here. So whenever we're doing these, and whenever we kind of have terms that we're working with, you kind of want to get it into the correct form, which is k times x raised to the power r. So I like to separate off the constant part from the variable part. So right now, and I want to write it as a product. So right now what we have is, it's kind of a quotient, which kind of makes the derivative a little bit more involved. So I want to rewrite it in this format where it's a constant multiple times a power of x. And the way we can do that is I can take this x cubed and I can break it off of the fraction, kind of pull it off to the side. So I'm going to pull off that x cubed and put it off to the side. And then I'm still going to have a fraction, but I'll have a 1 over 4 now in front. And so this is a property of fractions here, where if we have just some fraction a divided by b, we can always rewrite that as just 1 over b times the numerator. And that's what we did. I took the x cubed, kind of peeled it off of the fraction, and kind of put it right next to the fraction. But we still have a 1 up there. So we have this 1/4 times x cubed. And now, when we look at this thing, this is a good format for doing derivatives because we have a variable term and then we have a constant multiple term. All right, so how is this going to work? We want to do the derivative. So let's get the derivative of x cubed. So I'm going to bring down the 3. Keep x the same, subtract 1, so I get 3x squared. That's my derivative of the x cubed. And then that constant multiple, that 1 over 4, it's just going to kind of stick around in front. So I have 1/4 times 3x squared. And then if I want to clean this up a little bit, I would probably put the 3 and the 4 together, so I'd get 3 over 4 times x squared. And that's where I'd stop. Okay, so that's our constant multiple rule. And yeah, I think we'll maybe save the last few here for class time. But another one of our major rules, shrink this down just a little bit, is the sum rule. And this is another, like I said, it's another one of our basic rules, which is really going to kind of allow us to differentiate even more functions quickly. So what does this rule say? So it says we're trying to do the derivative of everything inside the brackets here. And what we have, there are 2 different terms. So there's a variable term f of x, and then another variable term g of x, and we're trying to add those, we're adding those 2 variable terms together. And we want to differentiate this whole thing. Well, what this sum rule says is we can kind of split up the derivative. And that's really what this says. We can split up the derivative over addition. And actually, this one also works for subtraction as well. So there's a similar rule for subtraction. So really, subtraction's kind of a special case of addition anyways. So yeah, so we have this rule, and what does it say? This is going to work for addition and subtraction. So we have two variable terms, f of x and g of x, and we're adding them or subtracting them. And we want to differentiate the whole thing. Well, what we can do, according to this rule, is that we can look at just the first piece on its own, differentiate it. We can look at just the second piece on its own, differentiate it, and then add the two results together. Or, if we're talking subtraction, then it would be subtraction there. So there's a similar rule for subtraction. So let's see this one in action. So as an example, we have x cubed plus 5x, and we want to differentiate this whole thing. So that's what this means. Differentiate everything inside the parentheses. So we want to differentiate all of this. And a lot of times when we apply the sum rule, we call this term-by-term differentiation. So essentially, we want to get each of our terms, we want to write them in that format where we have a constant times a variable. Then we're going to just differentiate each of those terms kind of on their own. And then we just keep the original addition and subtraction signs wherever they were. So the addition and subtraction they're kind of like the skeleton of our function. They kind of give us the framework, and then we're just differentiating the pieces almost. So let's give this first one a try. We want to do the derivative of x cubed plus 5x. So when I look at this, I see two terms. I have the x cubed, and then I have that 5x. And what we're going to do is we're going to differentiate first just that x cubed. So what do we get? Derivative of x cubed is 3x squared. So that's the derivative of my first piece there, my first term. So I have kind of two terms here. My first term, and then here's my second term. And now we want to differentiate the second term, and this is 5x. Well, the derivative of that is just 5. So my derivative of that second term is just 5. Again, if we're kind of just looking at this 5x, well, that's just 5x by itself is just a linear function, and the slope of that is just the number in front of the x. So the derivative of 5x is 5. And then because we had a plus sign there in the middle, we're going to have a plus sign over here in the middle for our derivative. And there we go. There's our derivative. So when we do these rules, even though they look kind of complicated, we're really not going to have, especially for these like polynomials, there's really not going to be much work that we show. We're just going to go right from our function and probably write down the derivative. All right, let's look at that second one. Actually, this one, there might be a step in the middle I would throw in for this one. So let's look at this one. X to the fourth minus 3 over x squared. So here we have subtraction, but the process is going to work just like as if it were addition there. Now, the one tricky thing is I would want to, first rewrite this function as kind of reformat this thing. So there's kind of a formatting issue here. So we want to get this k times x raised to the power r. That's the format that we want. So I want this 3 to be kind of like a constant multiple, and I don't want an x squared in the denominator. I just want a power function so that we can just use the power rule. So if I'm going to differentiate this, I'm going to first just rewrite the function just to help myself out. And what I'm going to do is I'm going to take this 3 that's in the numerator and just kind of peel it off of the fraction and put it in front there. So I'm going to have the minus 3 times 1 over x squared. Now that's pretty good, but it's still not a power function here. I have my constant multiple now. I have my 3 in front, so that part's good. But this 1 over x squared, not quite there, not quite derivative ready yet. So the next thing we could do is use a negative exponent. And I would rewrite that as what? Well, we're going to have that x to the 4th still. We're still going to have that minus 3. And then instead of 1 over x squared, I'm going to rewrite that as x raised to the minus 2. And now that's a good format for doing some power rule and whatnot. All right, so when I look at this, what do we have? I have 2 distinct terms. So my first term here is this x to the 4th. Just do regular power rule. My second term is this 3 times x raised to the minus 2. And let's see how the derivative would work here. So for the x to the 4th, just regular power rule. So I'm just going to differentiate that just completely on its own. So the derivative there would be 4x cubed. Then I want to get the derivative of the next term. Just do that completely on its own as well. So when I look at this, the 3 is a constant multiple. So that's just going to kind of stick there in front. And then let's put a nice set of parentheses. And inside the parentheses, let's do the derivative of that x to the minus 2. So we're kind of doing that constant multiple rule here. So how does the power rule work in this case? Well, I'd bring down the negative 2, keep x the same, and then subtract 1 from the exponent. So I'm going to end up with a negative 3 up there. All right, and we're just about there. Now with this sum rule, there was a minus in the original function as it was originally written. So after we differentiate, that minus is still going to be there. So there was a subtraction, and our derivative is still going to have a subtraction. And then from here, if we want, we could simplify it. And really, the only thing I would do is I would probably take this negative 3 and this negative 2 and multiply them together to get positive 6. So we end up with 4x cubed plus 6 times x raised to the minus 3. And that's where I'd stop. All right. So a little practice with, these are going to be our 2 kind of main derivative rules that we're gonna use these a whole bunch, and we're gonna kind of use them. We're probably gonna forget about them at times. We're just gonna always be using them, and so we'll practice a little bit more in class with these. But the thing to keep in mind is really what we're doing is we're kind of the addition and subtraction. They kind of give us the spaces in our function, and so the variable parts then are kind of just like the words of our sentence. And we're just going through term by term, word by word, and just differentiating each of those pieces on their own. And if we have a constant multiple, well, we have our constant multiple rule that says kind of forget about the constant for just a second get the derivative of your variable term, and then the constant multiple just kind of sticks around in front. All right, so we'll get a little bit more practice with these in class. So we'll see you then. Bye-bye.